Alex Matthews from the University of Cambridge talking about variational inference for Gaussian processes.
Okay. Can you hear me at the back? Yes? Good. Hi, I'm Alex. And as Sebastian said, I'm going to talk about what we think is quite a general framework for GP inference. So a bit about me first. So I'm actually homegrown as an undergraduate. I studied physics over in the Cavendish laboratory. And actually, to start with, I was mostly interested in quantum physics. But in my fourth year, I took David Mackay's information theory course. And that really kind of changed my path. And so instead of doing a PhD in quantum physics, I went to study, went to work at a startup, which was spun off from the University of Oxford. And while I was there, I encountered the work of Zubin Garamani, and I became very interested in it. So I came back to Cambridge to do a PhD with Zubin, which has been absolutely awesome. And I'm just finishing that PhD. Okay. So I'd like to talk about my co-authors. They are James Hensman, Maurizio Filippone, Richard Turner, and my supervisor, Zubin Garamani. It would be difficult in the available time to do justice to all the excellent work that's been done on this topic, but I wanted just to mention a few people, namely Michalis Tsitsias, Edward Snelson, and Matthias Seeger. Okay, so what can you do with the Gaussian process? Well, the GP area is really kind of a thriving area of research, and that's partly because you can do so many different things with them. So you can do spatial statistics. There you model the log rate of some disease using a Gaussian process. You can stack them and make a deep GP, and Tan gave us a very nice talk about that this morning. You can do Bayesian optimization, where your model for the unknown function is a Gaussian process. And for instance, in this paper, they were using Bayesian optimization to learn a controller for a robot, and that made the cover of Nature. You can use it inside an automated statistician, and led by Zubin, there's a lot of work going on in that direction in our laboratory. And of course, Carl gave an excellent talk, which is really quite related to what I'm going to talk about this morning, where he talked about state space models and a variational approach to that problem. Okay, so you get these challenges that crop up in GP inference all over the place. And there's two particular ones I'm going to talk about because I think they're the tricky ones. So in general, GP regression requires worst case order n cubed computation, where n is the number of data points. The second problem is that if your likelihood isn't a Gaussian likelihood, then the posterior inference isn't analytically tractable, and you need to do an approximation. Okay, so we've been thinking about this problem for quite a long time now, and we now have these three papers on the topic. And of course, I'm not going to be able to describe everything that's in those in this time. But we also have this, this software package, GP Flow, which is a Gaussian process library built on TensorFlow. And that really implements the work in those three papers. So what I have got time to do is talk a little bit about the general approach, the features it has, and maybe illustrate it with some simple examples. So the features that I draw your attention to before I get into the detail are that we face the order n cubed problem using an inducing point method, which turns the computation into order n m squared, where m is the number of inducing points. The approximation we use has the characteristic that it gets closer to the posterior as m increases. And we'll see in what sense I mean that as we go on. We can deal with non-conjugacy in the same framework, and it's all integrated. And we can go even more scalable than nm squared using stochastic gradient methods. And we're able to achieve all of these first four things in a way that will converge. So the glue that holds this framework together is variational inference. In variational inference, we have an intractable distribution p tilde, which is approximated with the distribution q in some variational family, big Q. We measure the similarity between those two distributions using the KL divergence, And that has lots of useful properties, the most important of which is that it's positive and it's 0 if and only if q equals p tilde. And what we're going to do is going to choose q hat, which is the q distribution that minimizes the KL divergence. Okay, so let's take a simple example. I've got some data here. You can see that there is some pattern in the data, but there's also some noise. Okay, and because we're being Bayesian, we're going to put a prior on the function that maps the inputs to the outputs. And so how do I actually generate from this prior? Well, I'm going to need some notation. I've got big X, which is the set of all possible input points. And I'm going to partition this X into 3 sets. I should say that at the moment I'm assuming X is finite, just for simplicity of exposition. And I'll talk about the more difficult infinite case in a minute. The partition that we have is into 3 sets, Z, which are the inducing inputs, D, which are the data inputs, and star, which is everything else in the index set. And instead of sampling in a big block that fx, we're going to break it up and we're going to sample it sequentially using the chain rule of probability. So let's illustrate that. So here, I've got 3 possible samples from the latent function values at the inducing point inputs. I'm going to choose one. And then conditional on that, I'm going to draw samples for the latent function corresponding to the data inputs. And there's 3 possible draws. And I'm going to choose one. And then this gets a bit busy, this plot. But I'm going to sample everything else, the starred set, conditional on the data points and the inducing points. And you can see by now that in many places, it's really quite well specified, the function. But further away from the points that I've already seen, we have some uncertainty still. And if we take a sample, then now we've really kind of pinned down this function. Okay? So back to the data. With the data is associated a likelihood, and that factorizes. And it's a simple application of Bayes' theorem to get the posterior. And what does the posterior look like? Well, here we have a posterior. Okay? Okay, in this simple case, it's analytically tractable to compute the posterior. But for larger data sets, we're going to need to approximate. And to do that, we're going to use a Q distribution that has this form. And what I want you to notice is that it looks like the prior, except we've replaced P of f of z with Q of f of z. And we're going to vary Q of f of z. So substituting that expression for Q into the KL divergence gives us a long expression. I'm sorry for all the equations. But what I want you to notice is that the blue terms will cancel and the red terms will cancel. And that's what leads you to a simple expression. These first 2 terms are going to be tractable. But this third term is this log of the marginal likelihood. That in general will be intractable, but it's only a constant, so it's not going to affect optimization. OK, so if I optimize my Q of f of z in the Gaussian family, I get a pretty terrible answer. The green is the ground truth, and the blue is the approximation. So what can I do? Well, actually, it turns out that I'm allowed to optimize the inducing input z as well, and that they are variational parameters in the sense that they will reduce KL divergence, and they're protected from overfitting. Actually, this was a sticking point in the literature. There was some debate initially as to whether you could do this, and it would be variationally protected. But the way to see it, in the way I've shown you, is that effectively the z is only really a label. Okay? So the underlying set, big X, stays the same, even if you swap your definition of z. And if I do that, then I get a much better approximation. The blue and the green line up much better. And you'll notice that the inducing inputs have moved towards the data. But this won't be the case in general. I'll show you some examples where the inducing points don't move towards the data. OK, so I should talk about this tricky infinite index set case that I mentioned, just because I don't want to mislead you that this is all super simple. I'm going to sketch it for the benefit of the people who have some background in the necessary mathematics, namely measure theory, but don't worry too much if you don't understand this. So we're going to have 3 measures, P, P hat, and Q, and they correspond to the prior, posterior, and approximating distribution. We're going to assume a dominating relation between them. Now, the first problem you have with the infinite index set is that the normal Bayes theorem won't work for you. So you need a generalization of the Bayes theorem, which is what you have here. The second problem you have is that the KL divergence that you would normally use won't work in this case. And there we need a different definition of the KL divergence. OK, so we've done that laborious work for you, and we've followed it through, and we found that it all comes out OK. You get a very similar answer to what you would if you'd done it with a finite index set. But I wouldn't assume that that was always going to be the case. It works OK here, though. So you can also do classification in this framework. So what I've got here is the orange points correspond to one class, the blue points to another. The black points correspond to inducing inputs, and the black lines correspond to decision boundaries. And going left to right, we're increasing the number of inducing input points. And the top row is what we're suggesting, and the bottom row is an established method, which is the generalized Fitzy approximation. And what we would claim is that for a smaller number of inducing points, you get a more sensible answer. So look at 4 or 16. But you can see that actually they both do OK in this 64 case. Also, in the 64 case for our method, look at where the inducing points are. They're near the decision boundary. So in this case, they're not just moving towards the data points. OK, the other thing that is really nice about this framework is that we can easily do mini-batch inference by taking a mini-batch approximation of this sum over data points term. And if we do that, we can go after really very large data sets. So here I have 6 million training data points. And the task is to predict whether or not a North American airline is going to be late based on some reasonable characteristics of the flight. The red line shows what you get from a linear classifier, which will run very quickly for you. And the blue line, or the blue lines, show what happens in our case. And the take-home from this, with the time available, is that it takes about 15 minutes for the stochastic gradients to get to a point where you're outperforming the fast linear classifier. I would argue that's not too long to wait. OK, so we can also do the famous MNIST digit classification data set. And for the removal of suspense, we're not state-of-the-art on this, and we're not claiming that. So you can see that sort of various deep learning methods come in very low on MNIST. Effectively, it's kind of solved for deep learning. And we come sort of somewhere in the middle. We outperform some reasonable methods. But our aim wasn't to get state-of-the-result arts on this. Excuse me. Our aim wasn't to get state-of-the-art results on this. Our aim really is kind of to show that you can get sensible results using the scaling approximation. Because, of course, 60,000 cubed is rather large. And we can do things like double the number of inducing points, and we still get about the same result. So we think this is a pretty accurate portrayal of what a GP will do on here. Also interesting from a scientific perspective is what sort of inducing points you get. So the inducing inputs in this case lie in the image space, so they're inducing images. And here we have a selection of them. But if we zoom in a bit to look at some of the particular inducing points, so we initialize using k-means, which will put the inducing points near the data input clusters. But again, in this case, we find that the inducing points move away from the input clusters to the decision boundaries. So these 3 digits started in the middle of the 6s regime. And in this case, it became sort of a 6-5 hybrid. In this case, a 6-4 hybrid. And in this case, a more extreme 6. And you can see the difference here, if that helps. OK, so that's a whistle-stop tour of this framework for approximate Gaussian process inference. I'd like to just, now you've seen it, reiterate the features that it has. We take the order n cubed complexity to order nm squared using an inducing point method. The approximation gets closer to the posterior as m increases. And in fact, not all methods have that property. The non-conjugacy is variational as well, so that's part of the same framework. And we can easily scale it using stochastic gradient methods. And we can do all of this in a way that's convergent. If you're interested in what you've heard, I would suggest having a look into these papers in some more detail. And also, our code is publicly available as GPFlow, a Gaussian process library built on TensorFlow. Thank you very much. That's all I have, and I'll be happy to take your questions. Zoom in.
So can we now do deep GPs in TensorFlow as well?
It's on the way, yes. It's not in the public version, but we've been playing around with it, yeah. Yes?
So are you saying that the inducing inputs are interpretable somehow, or like that they have some meaning, given that what you said about them moving away from the k-means?
I think, what I wouldn't jump to is a kind of an interpretation in terms of what you see in deep learning papers. I think these are different. I think since they're traveling in the classification case towards the decision boundary, you might think of them as being a bit more like support vectors, as in the case of a support vector machine. But actually, we have much fewer inducing points than you would have support vectors in this case. So we're quite fast at test time. Friends?
So I noticed that support vector machines were on the MNIST. How did they speed up support vector machines? What was the method that was used to get that result?
Oh gosh, I'm not so sure off the top of my head. We did repeat it, though. I guess maybe working the dual representation? Yeah. But I think it was, off the top of my head, tens of thousands of support vectors. And we had about 500 inducing points. So,
how parallelizable is the method? I mean, obviously you can compute the individual quantities in the mini batch in parallel, but then the updates of the after a mini batch would be still sequential, or is there some intrinsic feature in your method that you can exploit to do massively parallel computation?
It's a great question. The answer is very parallelizable. So we've talked about doing this sum over data terms using a mini batch, but of course you could distribute that sum over many different workers, and that's one of the reasons that we're pushing in the kind of the TensorFlow direction, is that we can exploit some of the computational power better, and TensorFlow will do some of that for us under the hood. Of course, as with all of these things, you have the synchronization issue that you have to update the gradients to be exact in any case at every iteration. And people go down the asynchronous route, of course.
Okay, if there are no more further questions, then let's thank Alex again. So now we have the startup talks. The first one is Ferenc Huszár, originally from University of Cambridge, but now with a startup called Magic Pony Technologies. And he'll be talking about generative models for image processing.
Yeah. Does it work now? Yes. Do I have to switch this to? Thanks. Hi, my name is Ferenc. I'm at this company called Magic Pony Technology. I'm not going to explain why this is our name now, but I'm going to show you a little demo video which explains what we are working on and what our company does. Hopefully I can show this in full res anyway. So what we care about is using the latest machine learning techniques to enhance the quality of visual data. So what you see here on the left is a compressed video stream, in this case of somebody playing a video game. And this is what you would normally see online if you have limited bandwidth or limited availability of high quality data. And on the right of this line, you see what we get when we apply our real-time machine learning optimized quality enhancer. I'm going to talk about this just a little bit, that this is essentially a convolutional neural net of some sort. But the key point is that this runs in real time on various devices, including mobile devices. So now you can, or we can, put this technology on your mobile device into your mobile app and enhance the quality of the visual experience people have with particular data. So this is showing an enhancement where you increase the quality of compressed content, but you can imagine this working in other kind of scenarios, making computational photography kind of applications, or making it high dynamic range, or upscaling it to 4K. So generally, we care a lot about low-level vision, which is the kind of computer vision where you don't care about high-level concepts so much like in classification, but you care about things like pixels and generating content that looks good. And so if this works, the method that you just show on the video is actually produced by this method that we are just about to publish in CVPR. And this is the main graph. So basically it shows that these are all the other methods that are known for machine learning-based video super resolution. So when you take low-resolution video and turn it into high-res. And this is ours. It's both faster and more accurate than all the others, basically. So this is the kind of plot that people like to have, I guess. But I'm not going to talk about this version. I'm going to talk about where we are going next, particularly in machine learning research. And this is a very high-level overview of the three things that determine the success of any machine learning application is roughly the data, the quantity and quality of it, the model that you have. Bayesian people tend to care a lot about this or spend most of their time here. And then the third one, which is the objective function, which encapsulates also the way you train this model, or you fit your model to the data. And what I want to argue is that for most of the low-level vision applications that we work on, actually the first two things are relatively solved. The models that we have, convolutional neural nets or MRFs, are roughly a good model for the kinds of things we want to do with them. The data is plenty and high quality, so there's no problem with that. But we really have a problem in understanding what the objective function should be. What does it mean for content to be high quality? And this is an example, which is work by Lucas, who's sitting somewhere in the audience. This is the original high-resolution content. This is a picture of Obama, of course. And then here we have the low-resolution content upscaled using this sort of baseline bicubic interpolation. So you can see that, obviously, a lot of the details are missing. And if you use the feed-forward approach that I showed you before, then you get a lot less blurry results. So this is, I don't know if you can see it on the projector, but it's supposed to look nicer. But it's also missing some of the features and some of the uncertainties and some of the textures, particularly from the image. And if you use a different way, and this is because this method was trained to minimize mean squared error on a pixel level, which is what most machine learning people end up doing. And it discourages the network to learn complicated patterns because it might incur a large mean squared error. Whereas an algorithm like this, which is based on something called neural style transfer approaches, will produce much nicer results perceptually, but it might incur a lot higher mean squared error. So if you just minimize the mean squared error, this solution, which actually looks much better, would be penalized. And you can see that it's not perfect because it also introduces some artifacts on the textures. But on the whole, the eye, for example, looks much more convincing on this one than on this one. So generally speaking, we are motivated to find new ways of training these image enhancement low-level vision models. And I'm going to talk about generative models, and particularly within this perspective of perceptual quality and producing nice-looking samples. So what are generative models? Roughly, they are models that you can sample data points from, sample data from that has, in some sense, similar qualities to the observed data. They have a wide range of applications. I think in this audience, I don't have to list them all. Some people use them for unsupervised feature learning and semi-supervised learning. but we are more interested in the applications in denoising super resolution things. Recently, there is a lot of renewed interest in using neural networks as generative models. So we've seen examples of variational autoencoders mentioned today. There's also generative adversarial networks, which I'm going to talk about. And then generative moment matching networks, which there was work from CBL, from Zubin and colleagues on this also recently. And I would argue that most of this success is driven by the deep convolutional neural networks' ability to represent visual information, pretty much better than anything else that we know today. So just a little bit of notation. I'm going to use these all the time, not particularly consistently. X is typically means an image or a data point. Q is a generative model, so this is a probability distribution. P is the real data distribution. E just means expectation. KL just means Kalb-Leiber divergence. I noticed that now making this curly is the new trend, so I might switch to that. And then Shannon's entropy is just H. The key question about generative models, particularly interesting when you use neural networks where none of the likelihoods or the normalization constants are typically available, is how do you evaluate and train them? And the key point that I always emphasize is that the way you train these generative models should reflect the way you want to use them. And in our applications, we can assume that we want to actually show these samples that the model generates to a person. And so our objective function could look something like this. We sample data from this generative model, and then we show it to a person, and the person evaluates how much they like this sample and gives it a score, S. So this is called an average perceptual quality. But if you only had this as an objective function, then the model would basically just always produce the nicest looking example, and it wouldn't have any diversity. So you might think about adding something like the Shannon's entropy of Q, which then encourages diversity of the samples. So that's what I'm going to be working with. For this scenario, when we care about producing samples that people like. So how do we think about S? S is called in the literature a no preference or blind perceptual quality score. To model this, we crucially need to understand human perception because it describes how human perceives errors that we make. The assumption is that the human perceptual system learns natural image statistics, so we are going to just assume that this S is well modeled as the log of the real data distribution. So the more likely an image is to be sampled in the real world, the more a person will like it. So if you put this back here, then suddenly what we end up with is this KL divergence, which is the objective function we want to minimize. And notice that this is different from this KL divergence, which is what people typically use when they fit a model using maximum likelihood. And I think this is also not surprising to anyone that these sort of known differences between the different directions of KL divergence, if this gray thing is your real data and you want to fit a Gaussian model to it, this is what you get if you minimize this KL divergence, so maximum likelihood. It tends to overestimate the probability mass, so it tends to produce samples that would never occur in nature. Whereas this KL divergence is very conservative, and it will only sample data from maybe one of the modes, so it underestimates the variance. But this means that it would never sample anything that a person would find unrealistic. So this more conservative KL divergence would be good for us to minimize. It's also very tricky to minimize this because in this case, we don't have any analytic handle on P. We only have samples from P and possibly only samples from Q. And one way to do this minimization is this recent method called generative adversarial networks. And by Ian Goodfellow and others. So this has two components. You have a generator network, which is typically a neural network that defines Q, the generative process, by first drawing some random noise Z and then squashing it through a neural network to produce an image. And then it also has a discriminator network D, which takes an image as an input and outputs a probability. And it's supposed to tell apart real samples from the real data distribution from fake samples generated by our generative model. And then the algorithm is iterative in a high level. In the D step, which is what I call this, we fix the generative model and we try to optimize the discriminator to do his job well. And in the G step, we fix the D, we fix the discriminator, and then try to adjust the generative model in such a way that the discriminator has a harder time classifying between fakes and reals. Now, it turns out there are multiple different variants of this algorithm. So this is the originally what they derived from theory, and then they introduced the second objective function, which is what they eventually end up using. You can also come up with another alternative step. The point of, and I'm not aware of anyone actually talking about this. Basically, you can show that if you use algorithm 1, then you end up minimizing the Jensen-Shannon divergence between Q and P. If you use algorithm 2, then we don't really know what this minimizes or if it minimizes anything, but it does work in practice. And it turns out if you use algorithm 3, then you end up minimizing KLQP, which is exactly what we wanted to minimize. So we can use generative adversarial networks to minimize the KL divergence. And it does produce pretty nice samples. So these are some manga characters and flowers, faces, even more faces. The problem with them is that they are really hard to train. So neural networks were notorious for having so many hyperparameters to optimize. Now imagine that you have 2 different neural networks that you have to optimize in tandem. So they are not exactly easy to get working. The summary, the pros are they have nice theory in the sense that you can get them to minimize KL or Jensen-Shannon divergence. It exploits convolutional neural networks, which I think is a key to their success. It produces nice samples empirically, and it only needs to sample from Q. To do this algorithm, you don't actually need to evaluate anything about Q. Only being able to sample from the process is enough. The cons are they are very unstable. It minimizes a lower bound. So that's not good. We want to minimize an upper bound or maximize a lower bound, but minimizing a lower bound is not good. There is no single underlying objective function that the 2 steps minimize. There would be, for example, an algorithm like EM. In this objective function, or in this algorithm, in one step you try to maximize something, and in the other step you try to minimize the same thing. So it's a little bit of a disconnect. And I'm going to talk about this property later. So we seek an algorithm that retains the nice properties, but is more stable or has better properties otherwise. And this is what I call the DGGM, the denoiser-guided generative models. And this is work in progress, so not very conclusive yet. So again, our goal is to minimize this KL divergence. And let's review in this light what the generative adversarial networks do. They directly estimate this log probability ratio from data. And this is not new. There's already literature on this. In domain adaptation, you also want to estimate these kind of probability ratios directly from data. So I'm just putting some references in here. It's called direct importance estimation or direct probability ratio estimation. And training a classifier to classify between fake and real images is one of the ways you could go about doing this. But there are other ways. You can use kernel methods. You can use all sorts of other ways to estimate this logarithm. The problem with the classifier approach is that although convolutional neural nets classify images very well, they are known to not represent the derivatives of the decision function very well. So this is an example that many of you might have seen. This is an image that the ComNet says is a panda. You add a little bit of noise to it, and then you get an image which to you still looks like a panda, but suddenly it thinks it's a gibbon. And to me, this says that basically the neural network learns a function that's not very stable outside where it actually sees any data points. So if you want to use the ComNet to estimate gradients, it may be not the best idea. And this might explain, I think, some of the unstable behavior that we see in generative adversarial networks. So what is the algorithm that I'm proposing instead? We still want to minimize this. And the first idea is that we don't actually want to estimate these log probability ratios. We only care about their gradients to be able to do optimization. But how can we obtain a direct estimate? Well, first of all, I'm going to rewrite this in this form. So you have the log q, the derivative of log q, and the derivative of log px. This is called score in statistics and also in machine learning and score matching. The second idea that this score, these log probabilities, the differentiated log probabilities, can be estimated directly using a denoising autoencoder. This is a known property of denoising. And the key idea is that if you consider the base optimal denoising function, what is the ultimate best denoising that you can do on images, it will turn out that the optimal solution will be this form. So if you try to denoise an image x, the output is x plus a constant times exactly this gradient that you care about. So the key idea here is that we can, instead of training a classifier to classify between P and Q, we can train denoising autoencoders that will give us estimates of these gradients that we are after. So this is the DGGM algorithm in summary. We start out by training a denoising autoencoder or any kind of denoiser function. It can be a Gaussian process. I don't care at this point, as long as it works well. It can even be a heuristic algorithm, as long as it's trained on examples from the real data distribution. And this denoising function will implicitly capture something about the data generating distribution. Then we repeat the following steps until convergence. In the D step, which is not discrimination step anymore, it's now denoising step, we train a least squared denoiser on Qt. So we have our current generative model Qt, and we train a denoising autoencoder to denoise examples sampled from our generative process. This is what I call denoise Qt. This is a function. And then in the G step, I update my generative model parameters using these estimated gradients. And this is what this algorithm will end up looking like, which I think is pretty nice to look at. So Gz of theta is one of my samples that I generated from the model. Essentially, the denoiser that's trained on P will try to make this sample look more like samples from P. And this denoiser trained on Q will try to make this sample look more like Q. And because of the negative sign, what this term ends up doing, it will try to push the samples apart from each other. So this term is trying to increase the entropy of my generative model, whereas this term is trying to increase the perceptual quality of them. So this is an example of such a method in training. Here, my generative model is a multi-layer perceptron. Z, which is the input to this multi-layer perceptron, is a 2D Gaussian. The denoisers that I use in the algorithm are also multi-layer perceptrons. This is very simple because it's just a two-dimensional data set. For the optimization, I use the ADAM algorithm, which is a variant of stochastic gradient descents. So you can see, if I can wait another cycle, is that the algorithm starts out by producing a lot of samples in the middle, and the first thing it does is it blows up the entropy. If you look for the next cycle to start, it'll blow up the entropy of the generative model until the variance roughly reaches the variance of my data. And after that point, it will start focusing on getting the details of the distribution right. So this seems to work, at least on this toy example. Here's another example. These are patches of grass image, because I live in England. And this is also the training process. So as the training converges, these fake samples look more and more like grass texture. This is, again, work in progress. It's not really using the full algorithm that I just showed you. But it's just to give you an idea that denoisers can also capture some of these statistical properties we care about. Another example with this candy texture. Again, it gets the idea that there should be colorful things, but it doesn't actually converge to really nice results. I hope that eventually it will. So if I still have time for a summary, the key takeaways would be that training a generative model should reflect how we want to use it. If your goal is to then use the representations in a supervised learning setting, then somehow your objective function should capture that. If you want to use the generative models to sample from them and show it to people, look how nice my samples are, then this is what your objective function should consider. And so here we care about a perceptual quality of the samples. Therefore, we kind of minimize this more conservative KLQP rather than doing something like maximum likelihood estimation. Generative adversarial networks, I think, produce nice samples partly because of this connection, as opposed to something like variational autoencoder, which tries to do maximum likelihood. So the question that I asked is, can we come up with a more stable algorithm for minimizing KLQP? The answer is, I don't know yet, because this thing isn't particularly stable at the moment. But the two ideas that I used is, instead of estimating the log probability ratios as the GAN thing does, I am going to estimate the gradients directly to reduce some of the noise. And the second idea is that to do that, I can use denoising autoencoders, or in fact, any kind of denoising algorithm trained on these distributions. And I think that the actual algorithm takes quite a nice form in the sense that you basically use denoisers to nudge the data points towards high probability regions and away from regions where you already generated a lot of samples. That's it. Question?
So we have time for questions? I actually have a question. So, I mean, it's absolutely exciting to see these samples, and it was a very nice talk. I just don't understand these methods. You can sample from them, but how would you use them, for example, in the compression video that you showed in the beginning? How could you leverage these models for the actual applications? Because essentially, it sort of ties your hands. You can only sample from them.
So the answer is that I'm not necessarily going to use these the generative models themselves, but what I am using is the idea of how to train a generative model, and that idea can transfer over to how do you train something else, like a model that does denoising again, which would be an interesting thing because I have denoisers in the algorithm itself. So that's the general idea, is that yes, these generative models cannot provide me with good probability estimates, but I can hopefully use the same ideas. If I can come up with a generative model training procedure that produces nice samples, then I can probably also come up with other techniques that solve those other problems using the same objective functions or the same ideas. Rich?
Yes, something you thought quite carefully about, the log P of data approximation to the perceptual quality seems a little bit problematic, because even in a typical set of images that we observe in the everyday environment, that log P is going to vary a lot, but I don't think the perceptual quality of Microsoft is necessarily more naturalistic than the mountains that lamentably I don't get to see very often. So whereas log P varies a lot for those two systems. And even if you do choose log P, it's still not clear to me that you don't want some hyperparameter that lets you trade off between log P and the entropy and sort of the correspondence to K.
Yeah, or at least, or maybe you could think about a monosodic transformation of log P.
Indeed. So could you just explore a little bit about the sort of sanity of that and how what happens when you don't get the K exactly?
I think that the motivation that this does something like a perceptual quality metric, I think is relatively weak. I think it's a nice story when you go through it, but obviously it breaks down because of exactly these kind of reasons. Also, why do you use this Shannon entropy? I just happen to use the Shannon entropy because I know that then my math works out. So in that sense, it's not particularly strong, but that said, if you actually look at the properties of KLQP, it still makes sense to minimize that as opposed to KLPQ, because the thing that you absolutely want to avoid is producing visual content that looks very, very unrealistic. So And this is what the KLQP's zero avoiding property will basically say. So yeah, I think that's a question of saying, you are right, it's a weak motivation, but actually you can motivate it by just looking at, look, this is what the maximum likelihood would do. It would tend to produce samples that are unrealistic if there is model misspecification. We don't want that. If you minimize KL the other way around, we might be able to avoid that. And that's basically I think maybe a stronger motivation than the perceptual. Zubin?
So if you don't want to produce images that are unrealistic, then I guess a limiting case of overfitting there is just to produce exactly images that you've seen before.
Yes.
So, you might not be able to produce Obama's face, but you just put somebody else's face there.
Yeah, I think that's a very good point. So
do you think that if you massively overfit this somehow, that could actually...
Yes, and I think that the community doesn't have a good answer for how do you characterize overfitting in generative models yet. So yes, these models, because particularly if you use very, very large neural networks, they could just memorize these things in their parameters. So one thing that people say in response to that is, look, we only made one pass of the stochastic gradient algorithm, and there's no way that, the algorithm only saw each image just once. There's no way it could have memorized it. So that's like a cheap way of trying to argue against it. I think that there is, similar to coming up with an objective function to how to train these methods, there's also a very interesting research direction in how do you characterize overfitting. And there's some recent work from Arthur Gretton on 3-sample tests, which I think has a lot of relevance in overfitting, a little bit like a generalization of cross-validation, but for generative models and unsupervised learning. So yeah, if you could solve that problem for us, that would be brilliant.
Okay, let's thank Ferenc again for a wonderful talk. So the final session of this the final talk of the final session of this workshop is again from a startup, or I think by now a well-established company, Cambridge-based, called Analytic, and the speaker is Sacha Krstulovic, and we will hear a talk about sound recognition.
Yeah, hi everyone. Can you hear me okay? Yeah, okay. Yes, I'm Sacha Krstulovic, VP of Technology at Analytic. Thank you very much for inviting us to this machine learning and artificial intelligence in Cambridge. We've seen, it's the end of the day, we've seen lots of very, very interesting talks and ideas about applied mathematics. This talk is going to be a lot more on the applied side than on the mathematics side. I hope you're going to find it entertaining and hopefully interesting as well. Oops. Okay. Right. So just a quick outline of the talk. We're just going to tell you a bit of about the context of what we're doing, which is automatic environmental sound recognition. We're going to focus on one particular aspect of it in this talk, which is performance versus computational cost. We're going to tell you a bit about the experiments we did, the kind of data sets we're using, the evaluation metrics we've used for this study, and then results and conclusions. I have to point out this work was a collaboration between Analytic and Queen Mary University and University of Surrey. So from the side of University of Surrey, that was with Mark Plumblake, who's here today with us. And then Queen Mary, there was Siddhar Sikhtera, who is doing his PhD on this topic, and then Adam Stark, who was a postdoc at Queen Mary at that time. So Analytic, what is it that we're doing? What is it that we're selling? We're actually commercializing automatic environmental sound recognition for the smart home. That means, so you're familiar with speech recognition and with music recognition. We recognize every other sound than speech and music. That's also known as audio event detection. What we detect is audio events such as a baby crying or a smoke alarm going off in your home when you're not at home, or glass breaks. We also have other sounds such as aggression, car alarms, gunshots, keywords, and many other things. Again, this is focused on the smart home. The application is you're not at home, something happens, the system hears it, and is able to send you an alert about what happened when you were not here to hear it. So how is that different from a machine learning perspective or classification perspective? How is that different from speech and music? Well, in the case of environmental sound, the data set that you're trying to separate, segregate, recognize is not as bounded as speech. So if sounds were vegetable, that's what would happen to your system. You're throwing all sorts of shapes and types and so on. The acoustic space of what can happen in a home is very, very rich. You have some beeps, you have some paralinguistic speech, such as people shouting or babies crying. You have crashes, knocks, which are sounds which were so far pretty understudied. You have broadband noises, such as your vacuum cleaner, your aircon, and so on. So it's a very, very rich feature space that you're trying to analyze and recognize automatically. There is no language model yet in the domain of the environmental sounds. I say yet because we have ideas about calculating the co-occurrence of certain sounds in certain scenes, but so far the data sets that are available for that kind of studies are not up to the task. So in theory, it's possible, but in practice, no one so far has a language model. Although we can have some, when we do testing, for example, in homes, we know that certain sounds are going to happen, some other sounds are not going to happen, but we don't have explicit models for that yet at the fundamental level. There is also another interesting thing is that there is a quasi-infinite priors on false positives. So your system is going to get exposed to a lot more other sounds than the target sound that you're trying to recognize. So if you're making a carrot recognizer, then your system is going to be exposed to 2 carrots versus lots of bell peppers and all sorts of other sounds. So there we go. That's a very specific problem to this field, where in speech you usually have the sentence which is triggered, the recording of the sentence is being triggered either by your phone service, you leave a voicemail, or by your keyword like hello Alexa or hello Cortana or whatever is going to trigger the recording of speech. So in our case, you get everything in the microphone all the time. Then there are also problems of far field capture and channel effects, which are similar to the things which are faced in the domain of speech. These require, so on the signal processing side, they require digital signal processing and equalization capabilities. But on the machine learning side, you also need a model which has good generalization capabilities. So what is the question that we're going to focus on in this particular talk? So for us, industrially, we need to use the algorithms which are going to cost the less in terms of computational power, because we need our systems to run on embedded devices. And so lots of people tell us, well, why don't you just use a cloud-based system? You ship your audio to the cloud and so on. The answer to that is very simple, is that because people mind the privacy. So it's better to have a recognition system running directly on your device, on your home camera or your home hub or whatever the device is going to be, than to beam the whole audio of your house to a server. So for us, it's very, very important to be able to run on embedded device. So we need to evaluate algorithms on classical axis, which is the classification error. We need algorithms to be good at classifying sounds, but we also need them to be good at classifying sounds at a small computational cost. So when we evaluate algorithms, we need to have that second axis of computational cost, which extends from very small stuff. This is an Arduino processor to Cray. If the algorithm is going to need a Cray to run, we just simply can't use it. So we have those two axes. The best algorithms are the ones which are doing a good job of classifying sounds at a low computational cost. The worst algorithms are the ones which need too big a computer to run and don't deliver very well. So we want to be as close to the origin as possible on that kind of graph. Now, in terms of comparing machine learning algorithms, we're comparing the usual suspects, which are Gaussian mixture models, which you're all familiar with, support vector machines, and deep feed-forward neural networks. We also give a shot at recursive neural networks because we're dealing with time series, so using recursive neural nets was also made sense in that particular case. So we did this experiment on 2 target classes, but we used 3 data sets, and I'm going to tell you why. So first data set was baby cry, so it was a simple problem of baby cry detections where we recorded tens of babies. We had 2 recording conditions, hospital and outdoors. Those conditions were spread evenly in both the training and test set. We had also a variety of recording devices, so a bit of channel effect in the mix. And we had so data sets which are pretty big compared to whatever was available as state-of-the-art before this experiment. So we have about 200,000 data points for the training set and 90,000 data points for the test set. Second experiment was smoke alarms, where we had 10 different models of smoke alarms for this particular experiment. That's a subset of our data set. Those were recorded in 3 homes, and 2 homes were used for the training set, 1 home in the test set. So the divide here is more an environmental divide. Those were recorded through an array of consumer electronics cameras. So we had up to 10 channels depending on the places where we recorded. We had this board where we had all these consumer electronics cameras, and we recorded through all of them, and they can sound very different. And so the training set again was pretty big compared to state-of-the-art sets for that kind of experiments. About again 200,000 frames for training and 100,000 frames for testing. Now, just to wake you up a bit, what do you think the third set was? Any idea, anyone? Okay, we call it the world set, which is a completely unconstrained variety of sounds and devices, and this potentially covers thousands of classes. So very often people misunderstood that kind of experiment, telling us, well, you're only dealing with 2 classes. Well, we're not only dealing with 2 classes. We're dealing with 2 classes against thousands of other sound classes which are being thrown at the system. And so the world set participates both into the training and the testing because we're training rejection models as well on the world set. In the case of Gaussians, you're going to have what's called a background model, which is trained on the world set, and then a foreground model, which is trained on your target class. In the case of neural networks, you're going to have different outputs depending on what if you're inputting one of the target classes or one of the world samples. And for support vector machines, you're drawing the margin between the world and your target class, essentially. Okay. Right. So I said this is a subset of our data set. So you can imagine the fun in recording data. We actually have hundreds of smoke alarms that we're dealing with. We bought every single smoke alarm available in the UK and in the US. There are interesting anecdotes about that in terms of some smoke alarms have an electronic component with a small amount of radioactive material in them. So we had to find ways to ship radioactive material from the US to the UK. There we go. So again, in terms of doing applied research, this is the kind of fun we're having doing products really based on machine learning. Right, so getting back to the evaluation and this axis of computational cost and classification error. So to evaluate the computational cost, we simply counted the number of operations involved into each of these models. So that's the GMM and then support vector machines with various kind of kernels, and then deep neural networks with various, with either sigmoid activation functions or rectified linear or recursive neural networks. And this is simply the number of additions, multiplications, and nonlinearities that you're going to have into these models, knowing that models with less nonlinearities are more desirable because nonlinearities, depending how you implement them, can be costly. So either you implement them with Taylor series, in which case they would be count for more than one operation, or you implement them with a lookup table, which can be approximated, can be counted as just one lookup operation, but cost you a bit more in terms of memory. So in terms of the cost of nonlinearities, we went the route of considering one nonlinearity is one table lookup. But generally speaking, you want the algorithm which is going to have the least nonlinearity as well. When it comes to sound detection performance metrics, so your error rate axis, there is one thing which is important to understand when it comes to detection systems, is the notion of trade-off between the false positives and the misdetections. So the way these systems works is all of them compute some kind of similarity score. So in the case of GMMs, that's your likelihood ratio between the target model and the world model. In the case of SVMs, you can use the deviation from the margin as a similarity measure. And for the deep neural networks and recursive neural networks, we had the single output, which was the class membership probability, which oscillates depending whether it's a target sound or not. So you have, I don't know how to trigger a laser. Anyway, you have this kind of score. The blue part is in a smoke alarm. You have the scores going down, so it's similar to a smoke alarm. The red part of the scores is the part where you're outside of your smoke alarm, and then scores have a different density. So the graph on the right is the red scores, densities of scores which are outside of your target labels, and blue line is the blue density is the density of scores which are within your target labels, in that case, smoke alarms. So what you can see here is that they overlap a little bit. So depending when you're going to place your threshold, which is that green dashed line, you're going to either have a system which is more conservative, is going to reject more sounds in general, so it's going to miss more of your smoke alarm. Or if you push your threshold up in that case, you're going to let more sounds go through. So you're going to have a lot more false positives, but you're going to miss less of your target sounds, less of your target sounds. So it's that notion of operation point, which is the choice of where you place the threshold to balance your false positives and misdetections, and that's application dependent. Also, that's the choice of the user where you place your threshold. Now, the goal is to compare the modeling power of these various machine learning methods, not the wisdom of the choice of the threshold. So instead of using final error rates in terms of false detection or misdetection rates, we use what's called the detection error trade-off curve, which is the results of browsing your threshold across your score densities and looking at every point, every compromise you can achieve. I'm going to show you dead curves in the next slide for you to understand that. The dead curves can be summarized into one figure, which is called the equal error rate, which is the location of the dead curve in the plane of misdetections versus false alarms. So those are dead curves. So you have the x-axis is the false alarm probability, the y-axis is the misdetection probability, and when you browse your threshold across all possible operation points, you end up with those dead curves. And what you want is you want your dead curve to be as close as possible to the origin. So the equal error rate is simply just a coordinate across the diagonal. So those are the results for this experiment across the baby cry class and the smoke alarm class. For the best model across a range of models, so we chose different neural networks architecture, different number of layers, different numbers of units per layer, and so on. For support vector machines, different parameters of pruning to end up with different amounts of support vectors, and so on. So when looking at the best model of each class between GMMs, SVM, and neural networks, in both cases, the neural networks did a better job than the support vector machines and the GMMs and the GMS. Now, in terms of what we really wanted to know from this experiment, which is so that number of operation versus performance, classification performance, we can see that the neural networks essentially achieved the best recognition results at the lowest computational cost, the lowest number of operation. The GMMs were still doing quite a good job in classification and at a low number of operations. And then the support vector machines were essentially all over the place. So conclusions. So on these experiments, DNNs, deep neural networks, appear to offer the best compromise between classification, performance, and computational cost. Depth matters. So the best models were actually the ones which I mean, you could have the same number of parameters with wider layers or deeper networks. So the deeper ones were achieving at the same cost were achieving the better results. Also, the nice thing is that the rectified linear units were best, which is good news because they're very, very simple non-linearity. So programmatically, when you implement them into an embedded system, they're very simple to implement. They really don't cost much. GMMs provide a decent low-cost baseline. So if your GMM system, if your system is a GMM system, it's still a valid choice. It's doing a good job, maybe not the best job, but still a good job. And SVMs were not really competitive with the other systems. That's it. Thank you very much.
Do we have time for questions? I have actually one.
Yeah.
So I would imagine that if you don't want to recognize a sound immediately, but you delay the recognition of a sound by 1 or 2 or 3 seconds or something, you can accumulate evidence and maybe make a more robust recognition of the sound. So in your particular applications, how critical is a time delay between the actual sound or event occurring and having to output a decision that this is actually happening?
Yeah, so that's true and not true. So for some sounds it's true, like if you have a detection of a smoke alarm, for example, you want that smoke alarm to have sounded for about 10 seconds before you send an alarm to someone because you don't want to react to simple beeps, for example, when the battery is off or something. You really want the event of a smoke alarm to be defined as smoke alarm sounding for a long time. Same story for babies. Now for some events such as gunshots, if you have a single gunshot, you have to recognize a gunshot. Glass break, same story. You're not going to have the thug trying to enter your home, hitting the window several times. They hit it once, it breaks, they're in. And so you want the latency of your system to be very small because you have also extra latency in the alerting system that has to circulate through whatever alerting system our customers are going to have in place. So we really have to react as fast as possible, but within the use case. So use case for the smoke alarm would be it has to have sounded for 10 seconds. For the baby cry, has to have cried for some time. And the some time, we define it as 5 seconds. Most people want to know, consider the baby has cried after it has cried for 5 seconds. So yes and no, it depends. Sometimes you can get the evidence. Sometimes not really. Sometimes you really need to have immediate recognition of your audio event. Yeah. Yes.
So you tried the RNN.
Yeah.
The DNN, is that based on a convnet for audio, or is it?
No, it's a simple feed-forward neural network. Yeah.
So have you looked at comparing the convnet to, like the convnets for audio to the RNNs, or is there any sort of receiver?
Yes, so we're thinking of looking at other architectures, so convnets and also the LSTM neural networks. But when it comes to the convnets, it's a model which is optimal for image, and there's not really any reason to think that convolutional neural networks apply to audio. So there is still that kind of fundamental question to think about, like, are they the right models for the right task? There is some hype around convolutional neural networks because in image they're giving those really state-of-the-art, impressive results. Are they going to be the best tool for audio? I mean, we have to have a look at that. Yeah.
So how do you think that you will have a better way of dealing with the scalability of data set collection? So if you want to learn gunshots, you probably don't want to do the same thing as you did with smoke alarms and buy all the guns.
So we hired them. We didn't buy them. we did hire a number of guns and went in different places and shot the guns as well. So we do a very fun type of work, which consists in breaking windows. And we again did break real windows. And we hired a hole in a former military base where they used to do the engine testing, and it's a hangar, and it's all soundproofed, and we were breaking windows in there. So scalability, I mean, each different sound class is going to have different fun. It's difficult to shoot guns inside a home, but you can shoot guns in places which model a home, so you can hire a shooting range and pad it in the way that would mimic the acoustics of a home. Yeah, data collection is fun. It's costly, but we're good at it, and we've had the kind of I don't know if it's courage or being crazy or something, but to go and record these sounds. Really, we don't take things from sound effects database. We do record real sounds in real locations. Is there a way to optimize that? I mean, no, you have to record these sounds. Someone has to do it. And we did it. And we're still doing it for new sounds and so on. So I'm not sure what could be done for making that less costly, to be honest. Yes?
Okay.
Zubin?
So how much of the performance do you think comes from different machine learning algorithms, and how much from the feature representation that you put in? So is there...
Very good question. In this experiment, we used the same feature set for all machine learning algorithms. So there was no... The algorithms were competing for themselves, not for the feature set. Now, it is true that different sound classes are gonna. I mean, recognition of different sound classes is gonna depend on different feature sets. You don't necessarily want the same feature set for something percussive, such as a gunshot, than for something tonal, such as a baby cry. Very true. The interaction between the feature set and the machine learning algorithm is one of these questions of meta optimization of some hyper something, which is the match between the machine learning algorithm and the feature set. In that case, it was both classes were tonal sounds. You had the babies and the things. So using the same feature set made sense in this experiment. But it's true that in our case, the choice of feature set makes a massive impact on classification accuracy. Absolutely.
Okay, great. Let's thank Sacha again for a great talk. And that concludes the workshop. So thank you all for coming. It was a great pleasure to host this event here, and I hope you enjoyed all the talks. Most of the talks will be available as video recordings on research.microsoft.com, but I will also send around an email to all the speakers. And if you check the workshop homepage, maybe in a week or two, all the videos will be linked there. So thank you very much, and I hope you enjoyed it.